Yeah. Hi everyone, it's Mahesh, Professor Mahesh Shirur. Okay, today I'm going to teach you the subject of applied hydraulics of Model 4 that deals with the hydraulic machine part 2. Okay, so in the previous session we have studied the impact of jet of vane curved when it is constant and when it is moving. Now I am going to tell you the force exerted by the jet on a series of curved vane. Here we are studying a number of series of curved vane which is attached to this shaft. In turn, this shaft is counted to the number of curved veins, and these veins, curved veins, are subjected to a impact of jet of water. Okay. In the previous session, we have studied the curved vein, but we have studied there only single, and here we are studying series of curved veins. The above figure or the figure shows the curved veins, number of curved veins which is attached to the shaft, fixed to the shaft, and the jet of the water from the nozzle, in turn from the pipe, hits the vein at a velocity v, and these are the curved veins, a series of curved veins which is attached to the runner outer part of this shaft is called as runner. To this runner the veins have been fixed. So from this figure we can observe that this is the curved vein, as in case of previous session. In that session there was only V here. In this session here it is V minus U. Due to the curve, a inclined line is developed which is known as V minus U. Then if it is inclined line or tangentially line, okay, meeting at with respect to horizontal at theta, this can be resolved into horizontal component and vertical component. The horizontal component is V minus U into cos theta, and vertical component is V minus U into sin theta. Okay, let D be the diameter of the jet and A be the area of cross section of the jet, and V is the velocity of the jet. Theta is the angle with which jet leaves the vane, and V minus U be the relative velocity with which the jet strikes the vane. Therefore, force exerted by the jet in series of curved vane in the direction of jet, that is in positive clockwise direction x direction, is given by impulse momentum equation as we used in the previous session. Momentum equation, that is force F is equal to, therefore force F is equal to rho into q, density into q, into v1 minus of v2. V1 is initial minus v2 is final. So F is equal to f of x. Force is applied in x direction. Then discharge q is equal to a into v, and v1 is equal to initial minus final velocity, and vt is equal to minus of initial minus final, that is minus of v minus u into cos theta, that is horizontal component. So v minus u into cos theta, here it is, see from this figure. Okay, minus sign means opposite to the flow. Okay, therefore force in x direction is given by rho into q is equal to a into v into v minus u minus of minus v minus u into cos theta. Putting the values of f, v1, v1 and v2 in this equation, we get the f of x is equal to rho into a into v into v minus u into 1 plus cos theta. Then we know that work done per second is equal to force into u, force into velocity in x direction. Then work done per second is equal to rho into a into v into v minus u into 1 plus cos theta. Therefore efficiency theta is given by work done per second divided by kinetic energy divided by per second. The theta is efficiency is equal to work done per second is nothing but rho into a into v, as in previous page, into v minus u into 1 plus cos theta into u, initial velocity, divided by kinetic energy is equal to half into a rho into a into v cube. So therefore efficiency is equal to 2 into u into v minus u into 1 plus cos theta divided by v square. After this further simplification, and I call this equation as 1. So this rho into v cube, yeah, said in previous session of previous, how it come, a rho into a into v into v, rho into v square, that v square into v is nothing but v cube. Okay, so this equation I will call it as 1, and condition for maximum efficiency is dou by dou u with respect to efficiency theta, that is equal to 0. So you have to differentiate above equation at one time. Therefore dou by dou u equal to this equation I will write here, v square equal to 0, and I will remove this 2 into 1 plus cos theta upon the square, and constant I will remove this. So dou by dou u equal to remaining as u into v minus u is equal to 0. Practically 2 into 1 plus cos theta and divided by v square does not equal to 0. Therefore I will take this term dou by dou u equal to u into v minus v square is equal to 0. Therefore, v minus, so if we differentiate with respect to u, we get v minus du equal to 0. Therefore, v equal to du. So I put this value in equation 1. Then maximum efficiency is given by 2u into 2u minus u into 1 plus cos theta divided by 2u into whole square. So further simplification you get theta maximum is equal to 1 plus cos theta divided by 2. Okay. So next one is force exerted by the jet of an stationary symmetrical curved vane getting hit at the tip. So this is the stationary symmetrical vane getting hit at the tip. So this is becomes the tip of that curved that in this is symmetrical, half of this and half of the veins is symmetrical. So if the force of the pipe of the water pipe from the nozzle hitting at exactly at the tip of this curved vein which is symmetrical, then what will happen? So at the stage 1 hitting, so this will be inclined line, that is velocity v resolved into horizontal and vertical component. So this is the theta with inclined to the horizontal, then that is called r cos theta, that is called to not r cos theta, it is v cos theta horizontal component and v sin theta horizontal component. And you can see also this is fixed and it is not moving. And at the this is at the entrance of the water jet, and this is at the exit of the vein where water is flowing out from the vein. Therefore this is v, and vertical is v sin theta and horizontal v cos theta, and this is theta value. Hence force exerted by the jet on the vein in next direction is given by impulse moment equation. Therefore F is equal to rho into q into v1 minus v2, where F is equal to f of x and q is equal to a into v. Therefore v1 is equal to v into cos theta and v2 is equal to minus v into cos theta opposite to the flow, that is called as minus. Okay. Therefore force in x direction is equal to rho into a into v. Putting these values in this equation, okay, v cos theta and v2 is minus v cos theta, that becomes rho into v square into cos theta. Therefore f of x is equal to 2 into rho into v square cos theta. Okay. Therefore force exerted by the jet on the vane in y direction, this is x direction and this is y direction, is given by impulse moment equation f of x f of y equal to rho into q into v1 minus v2. Here instead of f is f equal to, in previous case it is fx, and here it becomes fy, and q as it remains a into v, and v1 is equal to v sin theta in this case, and in previous case it is v cos theta, and in v2 is equal to v sin theta, in previous case it is minus v2 cos theta. So f of y is equal to rho into a into v. This v1 is v sin theta and v2 is v sin theta, and this also v2 is v sin theta. Okay, as it is minus minus, so this sin theta will get cancelled, so that into 0 is fy is equal to 0 and fx is equal to 2 into rho into rho into v square cos theta. Okay, next one is, okay, next one is when force exerted by jet on a stationary symmetrical curved when getting hit at the tip. Okay, this is stationary and this is stationary unsymmetrical. In the previous case it was stationary, here it is exactly divided by 2, it is symmetrical, and in this case it is symmetrical, stationary unsymmetrical curve. So this is not exactly, this line is not exactly half of this, okay, unsymmetrical curve. Okay, at that time what will happen? So this is the pipe object of the velocity v which is hitting here, and horizontal component is v cos theta, vertical is v sin theta. So this is at the entrance and this is at exit v sin theta, v sin phi. So at the entrance I will take theta, at the exit I will tell it is pi. The vertical component is v sin pi and horizontal component is v cos phi, and this is inclined angle with respect to horizontal is phi, and this is the velocity from here to here, it is phi, making an angle, tangential angle with respect to horizontal. So pi is the angle which jet enters the when this pi is here at the entrance, and this phi angle which leaves the jet of end, here it is this pi. Okay, so force exerted by the jet on the vane in x direction is given by F is equal to rho into q into v1 minus of v2. So where F is equal to fx and q is equal to a into v, v1 is equal to v cos theta and v2 is equal to minus v cos theta. v2 minus because opposite to the flow, therefore f of x is equal to rho a into v into v cos theta minus of v into cos theta. So this equation I am taking, I am putting this values here. So f of x is equal to force in x direction is equal to rho into a into v square into cos theta